Good afternoon. I'm Mike Duigo. I'm the speaker for this talk. I'm a member of the Java Core Libraries team. I work maintaining the existing collection libraries as well as I'm working on the bulk data collections extensions which are coming for Lambda in Java 8. This is a talk which is mostly about hopefully finding new things about the existing collection classes that you already know and use. It's not a tutorial. There's an assumption that you have had exposure to most of the classes that we're going to talk about, but hopefully we'll have some interesting things to say and some tidbits you may not have known before, or provide some new ways to think about the collection classes you're already using. In some cases, maybe provide alternatives to the choices you're making now with other collection classes that may be more suitable for the problems you're trying to solve. So we're going to cover some of the classes, or many of the classes, pretty quickly, and in not a whole lot of depth. We'll just be covering the more interesting points of the particular classes. And we'll take a small detour to collection classes outside the JDK. I will be posting the slides to my Twitter feed. There will be a link on there. I had it on the initial slide. It'll also be on the Q&A slide at the end. So all you need to write down is the Twitter handle that's on the very last slide. Everything that's on the slides will be there. As I said, we're going to look at the collection classes through the lens of the interfaces that the various collection classes implement. Many of the classes implement one or more interfaces, and interfaces are the normal mechanism used for describing how the particular characteristics of that implementation behave. So there may be more than one implementation with different behavior, different performance characteristics, different space characteristics, but they'll be generally categorized by a common interface that describes an overall set of common behavior between the various implementations. And we're going to be looking through the individual classes in the context of the interfaces that they implement. The collection classes that are provided by JDK come in two fundamental shapes. The first of these is what have as their root something called collection, which is just a group of objects. There's various ways that the objects are organized, aggregated, other properties to how they're handled, but fundamentally it's just a group of objects. The second shape in the Java collections is the map shape, where you have a pairing of a key object and an associated value object. And again, it's just an aggregation of multiple key value pairs. So those are the two fundamental shapes within the Java collections. We'll move on to the map shape, which, as we said, was a mapping of keys to values. Now, the keys in a map are distinct in that there's only one instance of a given key within a map. The values need not be. So in this example, we have two items which have a value of dairy. Both milk and cheese can be classified as dairy products, so that there's duplication of values but not duplication of keys. Beyond that, great. We'll see those slides again. Beyond the characteristic that keys are unique and values can be anything, not much is said in the basic map interface about the characteristics of the data. In particular, in basic map interface, what type of objects the keys are or what type of objects the values are is not part of the definition. The basic set of operations on a map are quite small. You can get an item by its key or get the value by its key, see if a particular value or key is contained within the map, remove a key, and then there's operations for putting key value associations into the map in either bulk or one at a time. The map interface, even though it doesn't have any direct association to hashing, is the reason that the hash code method appears on object. Many of the map implementations are in fact based on hash maps, and as a result, that's why Object provides hash code so that the map implementations which are based on hash maps can in fact utilize that in their implementations. One thing to mention about the hash code implementation, we'll make a few other comments about it as well, is that if you put an object in a map, it's absolutely critically important that its hash code value not change while it's in the map. The reason is that the hash map implementation will take the hash code value of a key, decide where an object goes into the map, and place it into the internal tables based on that hash code value. If the object's hash code then changes and you try and look it up again, it won't be found in the correct location in the internal tables. So you can in fact lose an object in a map if you change its hash code value or its compare to relation. So it's generally, well, it's absolutely necessary that you not change your hash code value for the object while it's installed into a map or a set. So the first map implementation we'll talk about is HashMap. And as we said, it's based on hash tables, and it is one of the implementations that uses hash code. It's backed by a bucket array. The location of an item's where an item is placed in this bucket array is based on its hash code. And one thing that's pretty important here is that because the map doesn't actually choose the hash code for an object, instead it relies on the object to provide a hash code value, the objects have to provide quality hash code implementations. If you defined an object whose hash code result every time was 4 and then tried to make a map of them, the map would still work, assuming your equals method behaved properly, but everything would end up in the same bucket. So high quality hash code implementations are absolutely essential for quality map or hash map performance. If you don't provide a good hash code, you're going to get order n behavior, in which case it's kind of questionable as to why you're using a hash map at all. One of the other things about hashing is that because the keys are stored into the bucket array based on hash code indexes which are essentially random, and there's something called rehashing when the table needs to be expanded. The iteration order of elements in the hash table isn't predictable. And in fact, in 7U6 and Java 8, it will become less predictable. So if your application has assumptions on hash map ordering, which as it turns out that there are a lot of applications that do, if the order of iteration changes either because the implementation of HashMap changed or because the table expanded at some unexpected time, let's say you had a table that for the last 10 years had 5 elements in it, and you were very used to those elements iterating out of that hash map in a particular order, and you add a 6th element, and all of a sudden the hash table's re-indexed, well, they now come out in a different order. In the 7U6, there's something called alternative hashing, which does randomize the hash locations. And we found that there were actually quite a few cases in JDK where there was code that had an implicit assumption on ordering of the results coming out. In 7U6 and later, it's going to become less predictable, so start looking at your applications for places where you might have either explicit or implicit assumptions on ordering. In general, as it turns out, the smaller and more stable a hash map, it's more likely that there's actually an implicit assumption. Examples would be things like service loaders, where it's loading services that have dependencies on each other. And if the service is loaded one time, you said, oh, okay, it works. If the iteration order now changes and the services load in a different order, there may be prerequisites that aren't met, and now all of a sudden the services crash. Yet that was a hash map with, let's say, only 5 entries in it. So it's not necessarily big hash maps that have that problem. Generally, when you get to a couple hundred elements, you no longer have a particular order for the elements in mind. So you stop making that assumption. But anyway, start looking for that in your applications. Linked hash map is a way to get a particular order to the elements in the map. And in fact, the order of the element iteration is the order that you inserted the items into the map. And linked hash map is most often used for LRU caches, so that when something is referenced from the map, you remove it and add it back in so that it's now at the head of the list. And whenever you run out of space, so you reference an item that's not already in the map, you eject the oldest item in order to fill the map in. Some people are surprised that even though the linked hash map provides an iteration order, it's not a sorted map. It could be considered a sorted map if you considered the sort ordering to be an off object, something that memoized the fact that what the insertion order was, but that wasn't deemed to be a priority for this particular structure, so they decided not to make it a sorted map. It does have an order, but that order is not a sorting. It's still nonetheless useful for those applications. Another type of map that's actually in JDK is WeakHashMap. It's also used for caching and like linked hash map, but a different kind of cache. Most often it's used for, in combination with soft references, where you want to cache something that if the VM runs out of space, it has the opportunity to eject it. Or it's caches for things that have weak keys, so that as long as nobody's referencing it, or as long as somebody's referencing it, you want kept in the map. But if there's nobody referencing it anymore, you want the whole thing to be garbage collected. WeakHashMap provides functionality specific to that. So again, it's primarily useful for specific cache uses. IdentityHashMap is a map which is really unusual. It's probably the most unusual map type. And the reason it's most unusual is that it doesn't use the equals operation or hash code in order to determine equality of entries. Instead, it just uses identity equality. And it's mostly used for very specific purposes of things like serialization, where you need to maintain an object graph. And another example is deep copy, where you want to not copy the same object over again. If you encounter it, you just want to insert a reference to an object you've already copied. Otherwise, you could have, if you had a list that contained another list that contained the original list, if you don't keep track of which objects you've already copied and link them back in when you make a copy, you just end up in infinite recursion of copying the same list over and over again. So IdentityHashMap is useful for situations like that. That was originally developed for, but there's one other common use for it, which is that if you have to associate some metadata with a particular instance of an object, IdentityHashMap is a good way to do it. So you make a map, an identity map that has the objects you're interested in and the associated metadata for that object in the value field. Very occasionally it's used for things like interning, but it's not always advisable for that, and you have to have kind of pre-planned ahead quite well in order for the identity hash map to be useful as an intern map. But occasionally people find the performance beneficial, sufficient to make the trade-offs worthwhile. Here we go again. That's one penalty of using VirtualBox to present from PowerPoint on a Mac, is that it sometimes misses keystrokes. Yeah, we're in the right place. EnumMap is a specialized map, which the key type is actually a Java 5 enumeration. And the reason you'd want to use this over a regular hash map with just the enumerations as the keys is that it's very space efficient. it essentially just has a table of the values for a table of the values, and doesn't actually have to store any of the keys. So if your key space can be described by the enumeration or already is an enumeration, EnumMap is a very useful thing. There's been requests in the past for this to be a sorted map because enumerations in fact do have an order, but that wasn't part of the original implementation. The choices to do that predate me, and I've never been able to find out why it wasn't made into a sorted map. But it's been requested, and it is possible that in the future it will be upgraded to a sorted map. Okay, so if you started with Java at earlier days, the map type that you used was called Hashtable, and it actually predates the collection framework and was retrofitted into it. The kind of subheading bullet is that some people still believe that Hashtable is faster, and generally they provide a benchmark that proves it. Most often these benchmarks turn out to be one of the two instances that they're comparing is rehashing one more time than the other one. And that mostly has to do with the thresholds that the two classes being compared don't have exactly the same rehashing thresholds. So one comes, usually it's to say, oh, Hashtable's faster. Well, if you look, it's at 10,000 items. Therefore, HashMap rehashed one time more than Hashtable. If you go to 20,000 items, now Hashtable has rehashed one more time than HashMap, and Hashtable's now slower. So be very suspicious of benchmarks where Hashtable comes out ahead of HashMap. In the general case, HashMap generally or almost always wins. As with any sufficiently complicated data structure, there's always corner cases where some alternative will win, but in general, there's no particular good reason to be using Hashtable anymore. In particular, one area where Hashtable is weak, and this was done in order to preserve iteration order from very early implementation, so that if applications had assumptions on iteration order, they didn't want to change those. So they didn't change the way key distribution is done. If you have a bad hash function, Hashtable ends up with far more collisions than HashMap, which kills performance. So in general, HashMap is going to have, or almost every circumstance, HashMap is going to have better performance than Hashtable. One reason people do use Hashtable is that all the external methods on it are synchronized. So you don't have to do the collection synchronized map in order to get a concurrent map. If in fact you're using a highly concurrent application, you should look at using ConcurrentHashMap instead. ConcurrentHashMap is similar in internal implementation to HashMap, except that the array that contains the hashing buckets has in fact been divided up into multiple segments, so that when you're doing operations on that table, or operations which mutate the map, the operations are redirected at a particular segment of the map. So let's say a map is divided up into 8 segments. If I'm in fact inserting in one and removing, if I'm removing one element and inserting another, it's highly likely that those operations will end up in different segments of the map. When that in fact happens, the two operations don't contend with each other for concurrency. The two operations can in fact happen simultaneously. So for higher concurrency applications, ConcurrentHashMap is a better choice than regular HashMap, or definitely Hashtable, there can be some surprising things about ConcurrentHashMap related to the basic HashMap type. One is that ConcurrentHashMap, like most of the Java util concurrent classes, is allergic to null. It doesn't allow either null keys or null values to be put into the map. There's a very common pattern which can be used, however, where you substitute an object that you create ahead of time for null within the map, if in fact you do need to install null into the map. if null is in fact your stand-in for your default object, it's better just to create a default object and install that into the map as either a key or a value rather than using null anyway. One benefit of not allowing nulls is that normally when you look at a regular hash map, if I say get key and the value that comes back is null, did that mean that there was nothing in the map for that key, or did that mean that the value for that key was in fact null? I can't tell the difference. With regular hash map, I have to call contains to find out if there was an association for that particular key. And if there is no if there is an association, then I can get the value and say, oh, the value is null. Because concurrent hash map can't contain null, if you call get and you returned null, that key's not in the map. There's a big difference between the iterators for regular hash map and concurrent hash map. Regular hash map iterators are something called fast fail, which means that if you create an iterator and start iterating, and meanwhile somebody changes the map, well, you get concurrent modification exception, indicating that the map state has changed while you were iterating. And the existing hash map treats that as essentially a programming error, that you modified it while you were iterating. Concurrent hash map doesn't view it like that. Instead, its iterators are consistent while you're iterating, which can have surprising effects in that if you do something like take the size of a map, create an array, and then try and copy all the elements into the array with an iterator, well, when you get to the end of the list of elements, you may already be beyond the end of the array, or you may find that you haven't reached the end of the array. The other example would be if you create an iterator, then call contains on the map for a particular element and it says no, and then you start to iterate through the elements, you may in fact find that element or not, because the map can be concurrently modified while you're iterating through the elements. As long as you're not assuming that certain things like the size of the collection don't change while you're iterating, or particular elements are in and out during the course of iteration, you'll be okay, but there's fewer assumptions you can make about the state of the collection while iterating using a concurrent hash map. Concurrent hash map implements a different interface than regular maps, which is called concurrent map. And the reason that concurrent map exists is because there are a couple operations that if they weren't defined in this concurrent map interface, you would have to enclose the concurrent hash map in a synchronized block in order to be able to do them. And these are all atomic operations that if I want to do something like check to see if a key is already in the map, and if it is, just leave it alone, otherwise put this key into the map, that's a two-step operation. First is check the map, do some Boolean logic, and then insert in the map. If I don't have this put if absent method, and I have to do it as two discrete operations, somebody may be able to sneak in between those two operations, and the answer that I come to won't essentially be correct. And the other ones, like remove a particular key if it has a particular value, also atomic operation, and the replace operations where I replace a key only if it has a particular value with a new value. Again, I would require multiple steps in order to do that operation without this atomic. And I definitely don't want to have to add a synchronized layer and on top of a concurrent hash map. So they added this additional interface beyond what basic map interface provides in order to provide these atomic operations. And there's actually two map classes, ConcurrentHashMap and ConcurrentSkipListMap, that implement this concurrent map interface beyond the basic map type. So another map type, extending the basic map interface is the sorted and navigable map. And the difference here from the basic map type is that the keys are now sorted. They have a particular order. In addition to the keys being in a particular order, the iteration order is now specified. So when you ask for the elements, you're going to get them back in their sorting order. There's not going to be a random, unpredictable order like it was for the basic map interface. But beyond the iteration aspect, the other key advantage to sorted map is that you can now create subviews of the map that make sense by specifying a particular key range, saying I want a submap that has everything below this particular value. Or above, there's head set, tail set, or head map, tail map, submap, specifying a range that you get a submap view out that is just the range that you specified. That is in fact a view of the basic map so that you can then hand that back to another piece of code, and if it makes modifications to that submap, they will be reflected in the overall map as well. So the partitioning features are actually quite useful for sorted maps. Oftentimes, you don't really care what the ordering is, but the submap, the ability to do partition submaps is just as useful as ordering. Now, I had on that slide, reference to navigable map, and there's two structures: sorted map, navigable map. Well, what's the difference? In fact, they're providing essentially the same functionality. Sorted map was around first, and then they decided that there was some additional functionality that they wanted, and they added navigable map in Java 6. Because of all of the existing implementations which provided the sorted map interface, TreeMap, etc., were in fact upgraded to the navigable map interface. So you can use those navigable map features on all of the classes which were originally sorted map, and they're quite useful. The example would be lower, which is that I want to find an element the element whose value is that's in the map that's the one next lower than a particular value. So if I say I want whatever elements in the map that's below 2.0, it'll hand me back whatever element that is. I don't need to know the exact value of it to extract that particular element. Previously, you would have had to do a head set or head map on the element with 2.0. You'd get back a map and then extract the last item from it. Lower is a lot easier than that. And again, because the existing classes were upgraded, there's no reason not to use navigable map in all cases. Unless you're still having to maintain with compatibility with Java 5, you might as well use navigable map in Java 6 and later. And you'll probably find that you can get rid of some crufty iteration code that was doing things like, effectively doing things like lower and inclusive head map and tail map that in the old sorted set interface. So one of the implementations of navigable map is TreeMap. It's red black tree order log n operation performance, as in contrast to the hash implementations, which are order 1. This is kind of a strange map in that it conditionally supports null. If you use it in the default sorting order, which sorts the items in the map according to the comparable interface, which is the compare to method, you're not allowed to use null because it's unspecified as to where null would fit in the sorting order. If you provide your own comparator function that handles null, then in fact you can use null in the keys for a tree map. But it is kind of odd for some people that sometimes you can use null, sometimes you can't with this particular class. ConcurrentSkipListMap is a concurrent implementation of the sorted navigable map interface. If in fact you're doing heavy concurrency, kind of along the lines of ConcurrentHashMap, it's a much better choice than using synchronized sorted map or synchronized navigable map on TreeMap. And in fact, if you have massive concurrency where you're have many threads modifying a map simultaneously, ConcurrentSkipListMap can actually be better than ConcurrentHashMap. And the reason is that the contention on nodes only comes down to the node ahead and behind a particular node that you're inserting or removing, whereas in ConcurrentHashMap, the map is divided up into segments. So the contention space in a concurrent skip list hash map is much narrower. But it does have a higher GC pressure for the way that it creates. If you're doing a lot of operations to insert and remove, it generates a lot of garbage, which is a frequent complaint by the people who use it for its high concurrency characteristics. But there's not really much in the way of alternatives because it is the highest throughput or highest concurrency or highest throughput it is the highest throughput in very high concurrency situations. And again, it doesn't support null keys or values like most of the other Java util concurrent implementations. So we started off with map, which was probably a kind of a strange place to start given this is a collections talk. We're going to actually talk about the collections classes now. A collection in its most fundamental state, it doesn't actually say too much about the objects that are in the collection. If we look at this example we've got on the screen here, we got fruit, bread, milk, meat. Are those items ordered? Do we know? Are duplicates allowed? Well, there aren't any duplicates in this list, but maybe they are allowed, maybe they aren't. Are these in fact ordered in any way? Don't know. The basic definition of collection is actually quite vague. And the set of operations that are provided on a kind of primordial collection is actually quite small. You can add an item to the collection, but what the semantics of add are is not completely clear. You can check to see whether something's in a collection. That one's pretty obvious. And you can remove items. This is one of the collection interfaces that has no actual implementations. All of the implementations for collections within the library actually implement sub-interface of collection. There is a type called a bag or a multi-set, which we don't provide an implementation for in the JDK that would in fact implement the collection interface directly. But as it turns out, as it happens, we don't provide that. So if you've got a collection and it's got a fairly limited operation, one of the key things about collection is that it's not defined by what it does, but it is a bit defined by what it doesn't. It doesn't say anything about ordering. It doesn't say anything about duplicates. It doesn't really say anything about mutability. And there's nothing really said about concurrency either. All of those decisions are in fact left to the sub-implementations. And if we look at an inheritance hierarchy, we can see all the sub-implementations that provide specialization of those behaviors and answer some of those questions as to whether duplicates are allowed, ordering, etc. But we don't need to look at this inheritance hierarchy just for the specialization cases. We can also look at it for the commonality that's expressed here. It is useful to, for example, pass something as a collection when I don't care about the, I don't want to expose the fact that I used a particular sub-interface like list or set. If all I want to do is find the intersection of two things, the fact that the implementation of those is a particular type may be irrelevant. So it's advantageous in some cases to ignore the differences between the actual specializations in order to have more generality of the operations that are performed upon it. And the most general operation isn't even in fact part of collection. It would be part of the iterable interface where it says just give me an iterator for those things. An iterable is kind of even a more primordial collection, and it doesn't even provide the opportunity to add and remove items or check for individual items with container or even compare two things. It just says give me a way to enumerate all the items in this container. And that's really useful to be able to enumerate all the things in the container. The fact that it happens to be an array list or a set or whatever, in those particular cases, I'm probably not interested in that characteristic. All I want is the items in the list. So there's advantages to the generality, and we'll look at shortly at some of those. First of them being that if you're doing variables and if you're defining variables and fields, it's advantageous to specify the type of the field as the interface rather than the implementation. The reason is that if for some reason down the road I wanted to change to a linked list or something like that because of some performance characteristic, I would now be free to do so. And if I had something like the next situation where I have specified an array list in a method parameter, I now can't use any of the other list implementations. I'm stuck with having to provide an array list, and it would be really inconvenient if I happen to have something in a linked list and this calculate method only took an array list and I actually had to convert the linked list to an array list in order just to pass it in. It's better to use the root interface type or go as generic as possible whenever you specify these things so that you have the widest variety of collections that can be used. One interesting trick that I kind of discovered over the last couple of years is that if you define an interface like this here where you have some method taking a type and returning a type, this looks pretty straightforward. I've avoided this problem of array list where I'm not specifying a particular type. The problem is that if I have an array list and I want to keep it an array list because I'm using it in a particular circumstance where the characteristic of the array list is important, if I have this definition of sort, the first definition of sort, what I get back is a list, and I can't assign that to array list anymore. I've lost the array list characteristic of it by calling this method. There's something you can do with generics, which is to say that A extends list of string, and then I say A in the return type and A in bar for the parameter type. Now whenever I pass a list to this sort method, the type that I get back from the sort method will in fact be the same type as the type that I passed in. So that allows me to do something like pass in an array list as list and assign the result to another array list. That can be pretty useful to not lose the type information that you had by passing it through a method. And you'll see that the JDK collection classes for things like sort in fact use this exact declaration of for return types that they generate. Summary of this kind of section is that if you don't need some characteristic of the particular type you're using, go for its more common ancestor. You're going to gain generality, which in the long run will pay off. So we're now going to continue through some of the collection classes. We'll go on with set. Set is a collection class that does not allow duplicates. For each item in the collection, it's only allowed to appear a single time. The items in the set are also not ordered. So in this particular case, we have a particular ordering of fruit, bread, milk, meat, etc. If I were to regenerate this set, they might be in a different order, but that doesn't matter, or shouldn't matter. Oh, here we go. I'm sorry about that. Well, quite a ways that time. There's not much to say beyond the fact that items are not ordered and the iteration order is not defined and there's no duplicates allowed. There's extensions of set which are the sorted set and sorted map that we'll be talking about. And one thing that's kind of neat about set is that there's a utility which a lot of the set implementations are in fact built on existing map implementations, like we'll see sorted map, etc. or sorted set that's built on sorted map. There's not a complete universal congruence in that there's not a concurrent hash set, but there is a utility which allows you to make a set from any map type. So if you have some other map type, you can make a set out of it. Specialized sets, we have an enum set. We've already talked about EnumMap. This is very space efficient for just enumerations. But if your data is not an enumeration, you can't use it. It essentially comes down to a bitmap, which for reasonable size sets can just be a single word, which is there's no external objects that are linked out like there would be on another map type. It's highly efficient. So if you haven't looked at enum maps or enum sets, go ahead. It actually supports enums bigger than 64 items as well. That's the second implementation. And in that case, it's an array rather than a single long for the bitmap. But enum sets are quite efficient. Hash set, we mentioned that many of the set implementations are based on map implementations. Hash set is in fact based on HashMap. Linked hash set is in fact based on LinkedHashMap. It's used in similar ways for LRU caches. We're going to move on to sorted set now. And like mapping, the partitioning is in fact one of the key values of having a sorted set. Not just the fact that the items are ordered, but being able to partition them. Tree set is the implementation of set that's based on TreeMap. It has the same restrictions regarding whether you can include nulls in it or not. If you provide a comparator that handles null, you can use nulls. Otherwise, you're not able to. Concurrent skip list set. It does have an association with concurrent skip list map. You don't have to use the collections set from map, but it is in fact based on concurrent map. Some of the surprising things about it, that are mentioned are that, like we had talked about with ConcurrentHashMap, the iteration, the things you're iterating can change while you're iterating them, not the individual element, but an item might not be there later on in the iteration that was there at the start of the iteration. One thing that's really odd about concurrent skip list set is that most people are used to being able to call the size operation on a collection and have that be a relatively cheap operation. For concurrent skip list set, it actually has to enumerate all of the items in the set. And because it's enumerating, it might change concurrently while it's happening in order to generate the result from size. In general, though, if in fact you are using concurrent list skip set concurrently, the size operation as a result is almost meaningless because you can't really say at what point did this structure actually have this size. Anytime you go back and look at it again, the answer might be different. So size is not only more expensive to calculate than you might expect, but it's also less useful with a concurrent skip list set. And that's also true of ConcurrentSkipListMap. We finally got to list, which some people may have thought we should have started there, but we wanted to mix it up a bit, so we end up with list nearer to the end. Unlike set, items are ordered. Whatever order you put them into the list is the order that they're presented, and you're allowed to have duplicates. List has some variety in its implementations, and one of the key differences between the implementations is that some allow efficient random access to the items in the list, others do not. We'll cover that there, but there's an interface that is used in addition to the basic list interface called random access to describe whether a particular implementation allows efficient access to indexed items within the collection. Array list is one of those random access implementations. It's probably the list type that most people are hopefully using in almost all cases, and hopefully very familiar to everyone. There is another array list, which can be a bit confusing, and this is provided by the Java utils array class, and this is actually a specialized list implementation for wrapping an array and then presenting it as a list. It's kind of odd, but it has exactly the same name as array list, and you can get the two confused on occasion, and that can lead for some head scratching because, in fact, arrays as list, array list has different capabilities than a normal array list. The most noticeable of those is the fact that its size is fixed. There's no way to shrink or grow it. The array that backs an arrays list can't be modified, or it can't be structurally modified, neither shrunk nor grown. You can still modify the list. So if you want to set a particular element to a different value, that's still possible with this type of list. But structural modifications aren't allowed. Be on the watch out for, if I'm having some problem with an array list, why can't I modify it? Why did I get a unsupported operation exception when I just tried to do something totally normal for an array list? Well, look at the class name signature and make sure that it's not one of these that someone snuck in on your code, because it certainly can be confusing. Yep. So we're going to jump fairly quickly here because we're running a little late, but copy on write array list is a specialized type of array list for concurrent modifications. The main idea here is that whenever the list is modified, a copy is made. And the advantage to this is that if you have a structure where you're doing mostly read operations and iterate and iteration operations, it provides a stable list that those operations will complete successfully. You're not going to run in concurrent modification exceptions, and other threads can continue to modify the list while you're iterating it. This does come at the cost of those modifications copy the backing array of the list, so that if you're making a lot of modifications on the list, it can end up being quite space inefficient. It does generate a lot of garbage. But if your usage is dominated by reading and iterating, copy on write can be very useful because it avoids having to block people who want to make modifications to the list until you're done iterating them, or having to make copies of the list just in order to be able to iterate it. Useful utility class. Vector is a counterpart to array list. Its main difference would be that all the public methods are synchronized. The performance trade-offs between it and array list aren't as dramatic as they would be between Hashtable and HashMap. In part, mostly because hotspot is magic. If an access is uncontended, hotspot is able to basically omit the synchronization steps that would otherwise be required. But there's not much good reason to be using vector anyway. You might as well just use collections synchronized list on an array list. Linked list is not backed by an array. Instead, it's a linked list of elements. It doesn't have a random access capability, so that if I want to index into the list to get the fifth element, I have to actually iterate through the first four elements in order to get to there. The main advantage to this is that there's no size bounds like there is with array list. And linked list also supports additional interfaces of Queue and Deque, so that it can have much better performance, or it has much more versatility than array list. We're going to move on to queues. Simplest one would be array Deque. It is reasonably space efficient, but it's not highly elastic. So if I have cases where the size of the queue grows and shrinks radically, array Deque is not going to be the best choice. Priority queues. The one caveat on priority queues that you must pay attention to, just like HashMap, is that if the priority of the item changes while it's in the map, you have to remove it and re-add it. The map or the priority queue will in fact be inconsistent if you change the priority of something while it's in the map. And the results are unpredictable, and this is one of the most common problems with priority queue is that somebody changed the priority of an item while it was in the queue. This is a specialized linked queue type. Mostly its advantage is latency. It's not a blocking queue. There's another queue type which is mostly used for concurrent operations, which is the blocking queue and Deque operations. And what's meant by blocking here is that if I'm trying to push an element into the queue and there's no space, I'll block and wait until space is available. The same happens on the removing elements from the queue or Deque, is that I will block until an element becomes available. Because I'm blocking, it's absolutely essential that this be used concurrently. If there's no one else coming to add elements to the queue or remove them, I'll end up blocking forever. So these blocking queues really only make sense used in concurrent situations. Oh, great. It actually killed the whole presentation that time. That didn't happen in any of the rehearsals, of course. Array blocking queue is the most simplest one. One characteristic that's important here is something called fairness. If I have many threads inserting and removing elements, let's say I had 100 threads inserting elements and one thread removing elements. In the random case, the threads which were trying to insert elements would dominate the behavior, and it would be difficult for the one that's removing elements ever to get around to removing them. The people trying to stick things in would completely overwhelm it. In the fairness, if you use that option, adding and removing elements is done in a round-robin fashion, so that the longer you've been waiting, it's first come, first served for adding and removing, so that you're able to make more progress in situations where it's unbalanced. It does have somewhat lower throughput because you have to keep track of what order the adders and removers arrived at the queue for their operations, but it does ensure progress in the unbalanced case. An alternative to the array one is a linked one based on similar to linked list. The main difference here would be that you don't need fairness because the add and remove operations happen at opposite ends of the queue, so that they're not contending with each other. Again, like the other cases of array and linked list, the main reason to use a linked structure would be the fact that this structure is unbounded or optionally unbounded. Delay queue is a specialized queue that you can't pop the item out of the queue until after a specified delay occurs. This can be used very much like a priority queue, but for time-oriented things. You set a delay of not before this particular time. So it's a specialized queue. Synchronous queue is, some people may not call this a queue at all. It's in fact a handoff mechanism where you in fact have to have a pusher, an element pusher and an element receiver in the same place at the same time in order for an element to be exchanged. There's no storage for elements. Elements don't sit in the queue, unlike all the other queue types. But this can be useful when you must know that handoff has occurred. When your thread returns, the item has in fact been handed to the other thread. So we're just wrapping up. The collections library is not going to be enhanced significantly in Java 8 to add new collection types there's going to be some performance improvements to the existing collection types, but the new area that we're mostly working on for Java 8 is to extend the existing collections to support the Lambda functionality, and that mostly involves extending the collections so that they can be sources for the bulk data operations, including, where appropriate, parallel operations. So when you get the collections in Java 8, most of the collections you're going to see are the familiar ones, but I don't know if hopefully you saw some of the Lambda talks and or checked out the videos later on, because when Java 8 comes around, you'll be using the collections that you've been using in a very different way and a lot more parallel than you have been using them in the past. So that's actually quite exciting coming for Java 8. There's beyond the JDK collections, there's some other collection libraries which I'll take a short moment to mention. The text in gray is quoted from the individual websites of the products. You can find them at the links, and if you need the links, don't try and write them down. Just get the whole presentation off my Twitter stream. Goldman Sachs has provided a very rich collection library. The one thing that makes it very attractive is that they have collections on primitives, which are somewhat more space efficient than the collections we're providing in JDK, but they're more specific, of less generality than the collections we provide. One of the criteria for JDK collections is that they have to be of general appeal. We haven't necessarily found a need for having a map that has keys that are only doubles. Goldman Sachs, on the other hand, probably has a great use for that. So their collections library has maps keyed by doubles. The primitive doubles, not the box doubles that you could use with a regular Java map. They have quite an interesting collection library here, and including some parallel implementations that use fork join. Another one which a lot of people have probably heard of already is the Guava collections library, which is provided by Google. And in fact, Guava's more than just collections. They're now branching out into files and preconditions, some designed by contract functionality, and character set mappings and other things like that. But there's some interesting collection stuff in the Guava collections that aren't part of JDK. There are a few things in Guava that we'll in fact be bringing into Java 8, but it won't be any of the big collection types that they provide. There had been a proposal to add some of them, but so far we haven't found any that we absolutely needed to bring in. So what we'll be bringing in for Java 8 is mostly just very small utility functions that we think are useful. And we'll go to questions. And that address right there is my Twitter stream where I'll be posting the slides. And you can also grab the links to the Guava and Goldman Sachs collections there. So if we have any questions, we have probably just 1 minute, unfortunately, but be outside. Go ahead. Sorry? Well, they're maintained. That's one difference. Trove does provide primitives collections, and there are people who are using them, but there hasn't been much maintenance on Trove recently. My understanding is that the Goldman Sachs guys think they're pretty close to Trove in terms of functionality, and they're doing maintenance and working on performance, more so, applying more resources to performance than were ever applied to Trove. Thank you.